It's my pleasure to introduce Brett Bednarcyk. I'll give you a little background here. Dr. Brett Bednarcyk is a material and structures research engineer at NASA Glenn Research Center in Cleveland, Ohio. For the past 28 years, his research is focused on developing and applying nonlinear, multi-scale analysis methods and tools for advanced composites and other heterogeneous materials. In 2015, he was awarded NASA Glenn's top research award, the Abe Silverstein Medal, and he is a fellow of AIAA. And on a personal note, I've been with Collier Aerospace, Collier Research and Development, for about 28 years, and about 25 of those years I've been working with Brett. So when we started, it was just 4 of us, and at that time I started working with Brett, and I can remember driving to UVA and working together, just these little intense work sessions, and he's been really good for our company. There's several things in the software that he had a big hand in developing. One is the bonded joint capability. Another is the thermoelastic formulation. And he's been a great resource for us. If I have a question about composites, I'll call Brett's one of the first people I'll call about it. And on top of everything else, he's been a great friend to me. So please welcome Brett Bednarcyk.
Yeah, so I met Phil and Craig in 1999 when they came up to NASA Glenn to give us a course on hypersizer. And at that time, the company was 3 people sitting here and Mark Pickenheim sitting back there. So it's really cool that they're all here. And we started working together. After I met them, we wrote a proposal the next year. And I was a contractor at that time. So it was a proposal to NASA and it hit. And you won't believe what it was. A big part of it was building piezoelectric effects into hypersizer. So somewhere in your code base, in one of your old code bases, there's probably these piezoelectric terms that Phil and I developed equations for, following Craig's formulations for all the smeared panels and all that stuff. And eventually, it was used by absolutely no one. So, but it was super fun, and it's been great. And it's going from 4 people to now this army of blue shirts here. It's just really great to see. So the latest thing, I'll be talking about the latest thing we've been doing with HyperX in my group at NASA Glenn. You see, there are quite a few authors here. Some of these people are machine learning and like AI experts that are working with us on materials. But basically, let me advance. What we're doing is developing a machine learning capability based on Bayesian optimization for optimizing the choice of laminate families in HyperX. And the idea here, and we've demonstrated this to some extent, you'll see in the results, enabling discovery of did I just mess something up? No. Enabling discovery of laminate families maybe you hadn't thought of, okay? And the application we're doing here is to a project, it's actually an aero project looking at cryogenic hydrogen storage. So it's a cryogenic hydrogen tank that we're applying this to, and we're using thermoplastic composite for this cryogenic hydrogen tank. So here's the agenda. I'll give some background information, the material modeling that we used to get ply properties. You'll see we didn't even start with ply properties. We started at an even lower level. The workflows, and I want to emphasize the workflows are with the main machine learning stuff we're doing here is hypersizer is directly in the loop. We're calling it over and over using the API. And the trained ML model, and finally the optimized cryotank design. So just some background on hydrogen tanks. First of all, pressure vessel classifications, they have these types. We're dealing with type 5 here. So you may have heard of COPVs, composite overwrap pressure vessels. Those have a liner, so they're type 3 or they're usually type 3. For this, there's no liner. So it's an all composite tank. It's called type 5. You see over, I keep trying to use the laser. So over here you see this is a diagram of a cryo tank. For this one would be for kind of what we're going after, which would be for long-term use, like in an aero application. You see it's got actually 2 tanks. There's an inner tank that actually holds the hydrogen, and this is at the high pressure. So this is the main structural part. And there's an outer tank as well. And sometimes there's a vacuum in between, so that may have to hold a vacuum, but the main structural component is the inner tank. So that's the application we're going to be looking at here. Space applications, you're probably all familiar with, hydrogen storage. Craig had used this one when he was advertising my talk this morning. I want to highlight this one because we actually used the type of laminate we made laminate families from the type of laminate that was developed or recommended based on this. This was a NASA Boeing composite cryo tank technology demonstration. It was about 10 years ago. Some of the people in the room from Langley may have worked on this. I see David Slate nodding. So, the end of this was that they designed it and built it, you can see, and it performed, it met the mechanical design specifications, when it was tested, but it did not meet the leakage requirements, okay? So it pointed to, okay, we need to do more to prevent leakage of the hydrogen in tanks like this. And this is one of the reasons we're looking at thermoplastics rather than this was a thermoset. Cryo tanks for hydrogen-powered aircrafts. I grabbed some, pictures of the concepts where the red is where the tank would go in these concepts for different configurations. See even blended wing body over here, which I think we're going to have a talk about tomorrow. I don't think I stole any of these from any of the presenters here, but if I did, thank you. I tried to give credit for where I got these from. But there's a lot out there in various companies going toward using hydrogen power for aircraft. So here's our model in hypersizer. Again, it's just the inner tank, so it's pretty simple, really. It's a 5-foot long tank. You can see the dimensions up here, 2-foot diameter with hemispherical domes on the ends, and we just divided it up into 3 zones. You can see, the barrel, a transition zone, and then the caps. The maximum expected operating pressure here is 150 psi. That's a standard for these type of tanks. And we have some load cases we don't have any flight load cases in here. They're all based on pressure and different conditions like, pressure warm, pressure cold, and then empty and all sorts of things like that. And you see there's 6 of them, I think. So that's the FEM we're using. We didn't use the machine learning to generate the FEM or anything. One of the team members made that. And then I wanted to say a few words about laminate families. I've really liked using laminate families in HyperX. So most of you are probably familiar, but this is an example of kind of what they look like. They have a master stacking sequence, and then each of the columns after that is a specific laminate that's a candidate laminate in the laminate family. And why they're awesome is because they're automatically producible as you go from different zones, because they all start with the same master stacking sequence. But you need to define the master stacking sequence in order for you to have a laminate family that can then be optimized using HyperX. This is a tool that some of you are probably familiar with for doing laminate family trades. I had done this. This was in my talk from 2 years ago, and you can pretty quickly do trade studies, but they can take a long time if the number of laminate families you're looking at goes up. And then, of course, there's no guarantee the user has included the best laminate families to even consider. So the idea here is to, as I mentioned at the beginning, potentially get machine learning to tell you what a laminate family is. That's the best that maybe you didn't even think of. I mentioned these specialized laminates. It's the specialized layups that were suggested by the NASA Boeing project from 10 years ago. I'm calling these cryolams just because I needed some way to refer to them. I don't think they called them that, but that's what I call them. They basically avoided using quads, the standard, because it's pretty well known these perform poorly in microcracking at cryo temperatures. If you look at the literature over the past, 15 years on these type of structures and materials, that's pretty well known. So what they did was they used angle pairs, starting from a low angle and then going up, as you can see here, just an example. And then in the middle of the laminate, they put a pack of thin plies, and that pack of thin plies was always 60, minus 60, and 0. And this is symmetric, so you can see the thinner plies there. So we're using this cryolam concept, trying to follow it, but employing some new rules in the Python scripts that are tying this all together, which I'll talk about the workflow. But that are defining these type of laminates. You don't have to use that. That's just what we used here to to start, because that was kind of the legacy of that project. So as I mentioned, we have a laminate family generator. We defined 4 sets of rules for generating these cryo laminate families. Basically, we have pairs of those angles being adjacent, and then repeating stacks of angles, and that's kind of shown here. And then we have another condition that's plus minus pairs are not adjacent, you can see. So we just have all the can't quite read that, plus, is that plus or minus 50? That's minus 50. So all the minus 50s are next to each other, then all the minus 40s. And then we also fully permutated this. So there's 4 sets of rules. And again, this is just something we needed some way to automatically generate these laminate families, and this is what we went with. But we want to go back and consider quads, doubles, and metalites is another derivative of double type layup. So there's a lot more space here we could look at. So the overall workflow. As I mentioned, we didn't start with ply level properties. I have a slide coming up on this, but prior to the optimization, not in part of the, not in the loop, so out of the loop, we generated our ply level properties using micromechanics. We used the NASA multi-scale analysis tool, which is software that does micromechanics simulations, including progressive damage, so it can predict allowables. And this is the Python symbol, in case anybody's not familiar with that. So we're using Python to do that automatically, but it's out of the loop. And then in the loop, we're going to generate training data for the laminate families using HyperX, and then the machine will have the Bayesian optimization algorithm for determining the best laminate family. And that's all that part to the right is going to be in the loop. So this is a slide on the micromechanics simulations, just real quick. The reason we did this is because we wanted to make these, even though it's a simple model, the finite element model is simple, we wanted to make it as representative as possible. So we wanted to use properties at the different temperatures. So those the material properties for thermoplastic composites aren't available at all those temperatures, but it just so happened that Michigan Tech had a project with NASA Langley, actually, where they were using molecular dynamics to predict the properties of the neat thermoplastics, 6 neat thermoplastics at cryogenic temperatures, room temperature. I think that's liquid nitrogen, and that's liquid hydrogen temperatures. So by using this, if we could then get ply properties using these, we could have all the properties we needed available, and also it's a pretty good one-to-one comparison among the materials, since they were all generated this way. Of course, you would, for a final design, of course, you'd do testing at the ply level and above, of course. But so we took this, we made all the volume fractions 0.6. We used AS4 carbon fiber for all the composites. As I said, we did progressive damage to predict the allowables. It does not consider matrix toughness, so this is one place we could sharpen the pencil here. We could use a damage model in the micromechanics that takes advantage of the toughness of the matrix to give a better prediction about what will perform our cryo. But so this step, LAMPS was used for, that's the molecular dynamics code, predicted the thermoplastic matrix properties, and then we used this model, this micromechanics model, to predict the ply level properties at these 3 temperatures. And then, so we had all that, and then we put that in Hypersizer as our ply properties for 6 types of composites, okay? So we have laminate families going in the optimization, and also the choice of 6 ply materials. As part of this, we connected the NASA Glenn Granta MI materials database with HyperX through, using HyperX's API. Well, actually, this did use HyperX's API, as well as the API available through Granta. But basically, this is going from Python to Excel to Python to HyperX to get these materials from our database into HyperX. So that's a nice connection to have anyway, actually, because Granta is owned by ANSYS now, so it's used by quite a few companies. And here's some details on connecting the Granta MI with HyperX. Oh, sorry. Yeah, okay, it's just going, okay, it's going through it, sorry. Yeah, so here's some of the script, some of the details on the script the scripting that's used. There's the laminate family going into the laminate family being put in automatically with the Python being put into Excel, and there it is going from the Excel into HyperX. And this step was done using the HyperX API, not with just not with human interaction going to the import. So that was all done automatically. So the materials definition workflow, kind of mentioned this already, but so LAMPS populated our Granta MI database with the matrix. Then we ran simulations. Again, this was all scripted, so this was done automatically too. Ran the simulations with NASMAT, and then predicted the ply level properties that were put back in the Granta database, and then they could go, from Granta to hypersizer, as I showed. Yeah. Okay, so moving on to the actual machine learning stuff. This is a general slide on Bayesian optimization workflow. The first step is you give it some initial data. It uses that initial data to train a surrogate. And then what it means by optimize is you may have seen, let me run that again. This little GIF over here, it's showing how this is what it means by optimization. The Bayesian optimization is choosing those points based on a trained surrogate model of what points are the best to be interrogated. And so it determines when you're going through the optimization, when you're going through the workflow, it determines the next best simulation it should perform in the space of all the options it has. So for us, this would be choosing the laminate family to try and the material to try and all that to get a good point. That's what essentially that's the benefit. That's what Bayesian optimization is doing. It's picking the best points based on a trained surrogate model, the best point that will give it the most information next. Okay, and it does it through if it already knows an optimum, its previous optimum, it's going to tend to look in that space, but it also factors in spaces that have not been interrogated yet. So you do this repeatedly until you've reached your objective, and then the idea is hopefully we've discovered a novel laminate family. So in HyperX, we're essentially, so what all this comes down to is in that slide I showed last time, HyperX is serving as the objective function here. The idea is we're trying to find the lowest weight, right, which is exactly what HyperX gives us. And that's basically used as the weight is used as the score in the Bayesian optimization. If we did put this in, I don't think it ever got exercised, but if it found a laminate family that gave all negative margins, it would put a penalty of like 100 on the weight. But we tried to make the laminate families, have candidates that were thick enough that never happened, and I don't believe it ever did. But since this is a HyperX conference, we put all the HyperX API functions here. I don't think I should go through this, but you see there's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 API functions that we needed to use to make this happen. So again, a little more on our specific Bayesian optimization workflow. We start off to get the initial data. I mentioned this on that previous slide. So what we do there is to get the initiation data, we just give it a random point. So it just the Python just randomly picks a configuration, throw it in, get the laminate family, import the file, and then use HyperX to get what the optimum is. And then we just do that 10 times with 10 random points, okay? And that allows the Bayesian optimization to get an initial surrogate model that can be used. And then after that, you do the real Bayesian optimization where we're using it's actually called the baby Python package. That's going to go as we do each iteration, tell decide automatically what the next best thing is to try in Hypersizer. And then, you keep doing that until you've reached your objective. So the design space in this study that we did, it's not that big. It's 312 configurations, laminate family configurations, based on those, those 4 different rules and the bounds we set on them. But essentially, what the Python's going in and applying that rule and generating a laminate family for each time it's doing iterations. So here, this is just some examples of 4 laminate family configurations. So you can see, like right here, you can see this has all of them have this that thin ply pack in the middle, and yeah. And then we have 6 different ply materials that were generated based on the 6 different thermoplastic materials. Okay. So after all that, this is the money slide. Okay. So these are the optimization results. What I want to focus on first is don't look at the dash line. I probably should add that pop up later. But so this is after the initial data has been given to it and it's been trained. These are the actual in the loop iterations. The weight of the tanks started out around 110 after the first iteration, then came down just a little bit after the second, then the third. You see here, and after that, it actually so it was tracking the global minimum weight, right? And then it decided to check a point that was not as good. So the iteration, the next weight from the next iteration went back up to 110. So it obviously didn't take that as the global minimum. So the global minimum stayed the same. Then it went up again. So the global minimum stays the same. Came down. Global minimum stays the same, and then basically after the 7th iteration, it found the minimum. Okay. It tried some more before we stopped it, but you see it was interrogating areas that weren't as good. Okay, so after 7 iterations, it pretty efficiently found the optimum. How do we know it's the optimum? That's what the dashed line is. We essentially took everything the same and ran every permutation of those cases to make sure it had found. Actually, we didn't know if it had worked or not, but you can see it did. It actually did find. We confirmed looking at all the data, it did find the actual optimum from all the permutations it had access to. So the matrix material was this Arkema helium thermoplastic. The angle steps between those pairs was 14 degrees. Among those 4 cases, it actually used case 1. There's the weight, and the minimum margin was 0.0585. So at the end of this, we have a closed design in HyperX that was totally generated by this scripting. So at the end of it, I just went in and opened the database, and this is what it was showing. So here's the minimum margins of safety. You can see they're all positive, and it actually didn't really need the transition zone. The transition zone ended up the same as. I can't really tell if it's the same which zone the transition went with, but you see the barrel is 41 plies. You'd expect that to be right. That's the higher stress region of a cylinder, and the domes are 13 plies. And you can see here's the laminate family, the helium material, and I tried to highlight the two laminates there that so you can see the stacking sequence with the middle thinner ply pack there. Okay, so bottom line is it worked. We demonstrated it. So I have 2 slides left. So the conclusions, just to reiterate, it's a first generation ML capability based on Bayesian optimization. It's all being driven by HyperX, and the only reason we could do this is because we have this nice API to interact and have these scripts. It was pretty straightforward to write these scripts to interact with HyperX. And this is really the first time we've done anything with the API. I've done stuff with plugins before many times over the years, but never anything with the API. We applied it to this cryogenic hydrogen tank, and we successfully determined the optimum laminate family in 7 iterations. The one thing that I said the objective was to discover a new laminate family. It's questionable whether we did that really, because we did we did, write these rules, right, up front that the script was interrogating every time it was running a new case, right? So it would be better if we did not rely on these predefined rules. And so what we'd like to do next is inside this Bayesian optimization workflow, use a genetic algorithm at each iteration to really come up, to use machine learning fully to define the new lamina family. And then I think we'd have this really, really being able to discover new lamina families that, had no input from the outside. So, questions?
Hi, Brett. Really good presentation. So it seems like the underlying model that you guys used was a Gaussian process model.
Yeah, that's right. That's what Bayesian optimization is based on.
Okay. So I have a first question. So you initially sampled the space with just random samples, but then you just refined it adaptively using that.
Correct.
Okay. And then the second question is, since the software provides manufacturability metrics like global apply scores, drop-offs, etc., would you consider adding a second output to track and then train with both of those and then do a trade-off of the two? Because it seems like it's biased towards weight.
Yeah, it's only using weight right now. Yeah, so yeah, we could definitely do that. I don't want to misspeak. Is that available through the API? Was there an issue with that? It's not available through the API right now, because I think originally we were talking about possibly doing that, but I think we would need to wait till the new version comes out that has that.
Thank you for the presentation. How much faster was this than the laminate family design study tool? If you have a good
We didn't use that on this, and I think there's some overhead from running the API. The HyperX people can correct me if I'm wrong. It seems like running things in without using the API would run faster in HyperX. But the true minimum thing took where we were still using the API for this. This is why it's apples to apples. That took it was overnight. It took 10 or 12 hours to get through everything, whereas the Bayesian optimization was this whole thing was 2 hours. So, but I think for this case, I would imagine if we just took that script, right, the script that generates the laminate families, imported them by hand into a database, and then ran it through the laminate family trade study, I believe that would be much faster than both of them right now. Yeah. So.
Thank you. Excuse me, sorry.
My question is fundamentally the stresses in a pressure vessel between the hemispherical portion and the cylindrical portion about 2 to 1. What do you attribute the 4 to 1 thickness difference to?
Yeah, I don't really know. It's 2 to 1. It's 2 to 1 between the axial in the barrel. It's 2 to 1 between the axial and the hoop, right? I didn't even know that that's true. That you're saying it's 2 to 1 between the hoop in a sphere versus a hoop in a cylinder, right?
Yeah, it's PR over T and PR over 2T.
Okay. Yeah. That's a good question. Yeah, we should definitely check that out. I mean, the angles are different, you can see.
Is that maybe an area where you would want 2 different laminate families, a laminate family for the barrel, which is more hoop, and then a different family for the spherical part?
Well, don't we want to keep them compatible, right?
Well, yeah.
So then I'd need to use your other tools to make them compatible.
True, but that would answer
Yeah.
the question as to why
Yeah, the thickness is not 2 to 1, you're right. That's a good point, thanks for pointing that out. Oh, Craig was asking if it might be, if it might be a better approach to use different laminate families for the barrel and the domes.
Your 2 to 1 implies it's quasi-isometric, so you have a lot more strength in one direction.
No, I think it's statically determinate, 2 to 1. I mean, if you, a cylinder versus a sphere, I think he quoted the correct formulas even, and there's no material properties in there, statically determinate.
Really quick, what was the total number of parameters in your model, and did the Bayesian optimization struggle with the dimensionality of it?
No, it was fine. Yeah, I'm not sure. That's probably something we should have put on, the total dimensionality. But yeah, no, we were surprised actually, or not me, I mean the co-authors who are ML experts were surprised that it worked. It worked basically without a hitch as soon as we hooked it up and got everything working. And thanks to August, actually. August gave us a consult to make, there was one last hurdle we needed to get over with the API, and August helped us out with that.
I'm curious how the main stacking sequence came about, if it was a naturally occurring, because I'm seeing like a double sort of combined with a
Sorry,
spiraling.
can whoever's talking raise their hand? Oh, sorry.
Yeah, I'm wondering how that main stacking sequence came up, or the laminate families. It looks like a double combined with like a spiral approach.
Yeah, it's based on those laminates that I talked about that I was calling cryolams from the Boeing project. They knowing what laminate they used, they used these pairs of angles and then that middle ply pack of thin plies, right? So we tried to, make rules for generating laminate families that were like those. And so we came up with those 4 rules and let it rip.
I see.
So yeah, but as I said, it's just one option, right? You could throw more in there and let it trade out.
That's a better sort of sequence for the cryo specific kind of.
That was a conclusion. And is David Slate still here? No. I think they did testing on laminates in that project early on that they had reasons to believe that that type of stacking sequence, certainly you can imagine the thin ply pack in the middle would help with permeability because you have smaller cracks that happen if it does start to crack up, right? And that makes the path more tortuous. But I don't know the details of how they came up with that type of stacking sequence.
Thank you.
Did you have a question? Oh, sorry.
Yeah, what kind of failure modes were you checking?
Yeah, we used all this standard stuff that comes in the aerospace template. It's ply by ply, if that's what you mean, but we basically left all the standard ones on that are on by default. Yeah, so it's checking all of those.
And was it, I guess, difference between fiber failures and matrix failures? Were they, was it mostly matrix driven, or?
It's hard to say because it's looking at thousands and thousands of candidates, so I'm sure some were some way, some were the other,
Right.
You mean?
I just didn't know if
final case in the final design. I didn't look at what the controlling failure method was.
Yeah, I guess where I was going with that, I wonder if it was both of those failure modes based on the fiber orientations were very close together. Near zero for both matrix and fiber failures. So.
Yeah, it's not. I'm not sure. Yeah, I'd have to look at the margins, but. Did you have a question, Phil? No. Okay.
So first of all, I would like to give a genuine thanks to all of the presenters today. I think they did a most amazing job, and it does personally make me feel very proud to see the work and the willingness of them to be here with us, to share how they used our software and to talk about their application. So anyway, I just want you to know that Collier employees all really appreciate. There was one guy here I want to mention, Jonathan Russell, the guy from General Atomics. I understand left at 5 a.m. yesterday and just arrived, a few hours ago. It was a 30-hour journey, I think, for him with the bad weather. So we realized, it was a commitment of time to do this for us, and we really do appreciate it. And true that for everyone.